Video for class 12. I actually already gave this lecture yesterday, but I didn't have a video for this introductory stuff, so I'm going to repeat some of the things, just I have it for completeness. Alright, so in class 12 we make this transition from stuff that we've maybe covered in mechanics and materials, and we added some things to mechanics and materials, but here's like some completely elements of mechanical design content, and it introduces one of the most important features of the course, and that is the safety factor. Also the design factor, and we also have discussions of reliability, and we start to get into statistics with this. And I asked this general question: why do things fail? And I like to see what students come up with. And my second question is, what is considered failure? So I'm going to give you what my standard answer for this, right? So I think the book actually says the same thing, so it's not me coming up with it. But it's, I would say, why do things fail? Well, maybe we'll say this: loss of function, right? So that maybe that's the thing that we have to, instead of why do things fail, let's say you can say that they break, right? One example is overstressed, right? Something gets overstressed, which would mean that it has more stress on it than it can handle, right? But we we have to define what we consider failure. One thing that I could say, sometimes we'll say the yield strength, right? The yield strength is maybe the thing that we often will say, make a comparison and say, hey, if the stress goes above the yield strength, that's considered failure. But that's just going to mean we're going to have permanent deformation, right? It's not going to bounce back to its original shape if it goes beyond its yield strength. And that might be failure, and it might not work anymore, right? If it's I don't know, a crutch, right? You bend the crutch, it's not going to work very well. That's loss of function. Yeah, it doesn't work anymore. But if it's a fender in a car, right? You could keep driving in many cases if the fender gets dented. But if the dent starts to rub against the tire, then we can't drive, right? We have loss of function. So we have to come up with some kind of like premise, and we have to make a decision that beyond this certain limit is our what we consider failure. So we have to start thinking about those terms. Now, for mechanical engineers and many other engineers, the thing that we have here when we're making these decisions about loss of function, we also comes down to a competition between stress and strength. And I like to keep asking the same question over and over again: what is stress? And my go-to answer is the distribution of internal loads. The distribution of internal loads. So we've applied some kind of load onto the body, and it's trying to hold that load, right? It's trying to absorb it, and internally to the thing, it is holding the stress. And so we kind of try to think and picture what that stress is, right? The simple answer is F over A, or maybe it's bending, MC over I. But trying to picture what it actually is kind of an important type of thing. You could think of like these little particles, right? You get down to and they're like pulling against each other, right? Because of the other particles around them. Well, it's being distributed throughout this the body, right there. That's what the stress is. And strength right here is really going to be the capacity. The capacity / limit of stress in the member, right? So how much stress can it handle? But it depends on what the criteria of that is, right? And so our two big ones that we have for us is going to be the yield strength and the ultimate strength, right? And I'm using this stress strain curve to try to see. We note that like we have a definition for the yield strength, which is like an offset, a parallel line offset parallel with the linear portion you'll see they have this PL, that's the proportional limit. You also see we have the elastic limit, but we've decided that, like, you know what, let's go ahead and make this definition where we're going to have, I think it's a 0.2% offset. I think that's right. Yeah, that sounds right. In terms of strain, like we offset this, and where the intersection of it is, that's what we define as the yield strength. We can also see that we come up to this very ultimate stress, right, at the very, very top right here, and that's when the thing breaks. So this the difference between the yield strength, right? So we have the yield strength. Let's see, yield strength is one of them, SY, and then we also have. This is when it doesn't return back to its original shape. In fact, interestingly enough, it's going to climb up this curve as you applied load. It's going to get here, and you release the load. It's actually going to come down in a different path, parallel. It's interesting, isn't it? Anyway, but it's going to have some a strain that doesn't go away. Right? Usually it's going to come up, and maybe it'll rebound a little bit, but it's going to come back, and it's not going to get to the original size that it was. That's the yield strength. The ultimate strength, though, is when the thing actually physically breaks apart. Now, actually, technically, that's at the fracture strength, but most of the time, and we'll see over here in just a second, they're going to be pretty close to each other. It's like a minor point, so we can just go ahead and assume that ultimate means the thing actually came apart into pieces. So that's the ultimate strength. Ultimate strength. I'm going to spell it wrong. And most often, we're going to deal with the tensile strength. So sometimes this will be called the tensile strength. So it says the ultimate strength in tension. We'll find out that there are materials that have different compressive strength and tension strength. Most of the time, it's going to be stronger in compression than in tension. We'll talk about examples of those coming up. One really important thing, there's two different curves right here, and I have to ask in class, like, what do you think the difference is right here? And the answer is, this is ductile, and this is brittle. Right, so ductile can do a whole lot more strain. It's like wacky taffy. You can pull this thing and it's going to stretch out right here. Brittle, you stress it and snap. It's going to break apart. Right? It can't be pulled as much. And if these were the same value, and I could probably have scale this up so they actually come up to the same value. So if they both have the same strength, what we want to take a look at, we can see that the area underneath this curve is often referred to as the toughness, right? And that is a good kind of like indication about how ductile or brittle something is. But it's also a really important thing. It's strain energy, right? So if we were taking the area of something, we're multiplying the x by the y right here. Well, if we had like US units, but maybe let me just go like force over length squared, right? Times length over length. But we know that that energy, a particular kind of energy, work energy, to work something, is force times its length, right? So right there is energy, and right there under the denominator is volume, like length cubed. So we have energy per unit volume. So it's like energy density. That's how much a material can handle. This can handle a lot more strain energy than the brittle can. It's kind of an interesting thing. But now we start to think about stress as being like the strain energy that's being held into a body, like a spring. How much springiness can it withstand, right? That's the potential energy, and this is per unit volume. That's the same idea that we have in there. So we're kind of thinking in those terms. We also want to point out that this is engineering stress and strain. So we got this funny little thing going on where they got the fractures less than the ultimate. But it's not really, because the area that we're using to make that stress is based on the original area, but we know the sample actually necks. It actually gets smaller, so the real stress is it will actually climb up higher before fracture. Notably for brittle, they're pretty much the same. we don't have that necking type of problem right here. So just this is details that are important, yes, but for us, our main concern are these two strengths, yield and ultimate. And when we go about doing analysis of something, or we're going to evaluate something, we need to be clear under what basis we're talking about. Is it based on yield or is it based on ultimate? Right? And it tends to be for ductile, where we usually use yield, and for brittle, we usually use ultimate. Not 100%, but pretty much. The next section on here is a really important thing, where we're going to introduce the safety factor and design factor. Sometimes we use them interchangeably, but they actually are two different things. We have to, and they're there to address uncertainty. So I'm kind of answering, what can we do to account for uncertainty? You know what the answer is. But I said list some sources of uncertainty regarding stress and strength, right? So one of my first ones that I usually go is material. All right, now lots of things about the material. Like material unknowns, maybe is what I say. There's variability. We get a book out, we get a value out of a book, maybe, and say this is what the strength is, this is what the elastic modulus is, so on and so forth. But are we sure? What foundry did it come from? What day was it made? Out of a batch. If you pick one out of a batch, does that mean everything in that batch is going to be the same? There's some variability in there. There could also be defects and stuff inside the material. A lot of other stuff in there. Another one that I would put right next to it is like the effects of processing. All right, so we are going to take this material and we're going to do something to it, and that's gonna, and we're gonna make something out of it. I should say, right? And some of those things can be predicted. Some of those things might be known, but some of them might not be known, or we might have to be clear. I think the one that jumps in my mind is the HAZ due to welding. It's just an example of something that maybe we want to, there's some uncertainty in there, and that's the heat affected zone, right? And that happens when you weld something. Just think about it. You're melting the metal in the local spot, but all the metal next to it gets really, really hot. And what do we know that makes the metal, stronger? Heat treatment and cold working, other things like that. But when we melt it, we reorganize all those grains. So and then cool it down again, the rate at which we cool, we know that's where we have grain growth right there. So all the area, all the location stuff that's right next to a weld, all that heat treatment went away. It's got different grain structure right there. So all of a sudden, the strength that we are relying on in a local place, we don't know that it's true for sure. I'm gonna say, like, I wrote how stress is calculated. How stress is calculated. All right, calced. The model. And by the model, yes, I might mean a computer model, but also just making a little picture of the thing and putting some forces onto it. That's a model, right? You're simplifying the object inevitably, and to simplify the thing, how you calculate the stress from that, and the simplifications that you make are going to create some uncertainty. I think really big one that I would say, loads. Like the forces that you make, and then maybe you could say that's still how stress is calculated. The model, loads, the magnitude of the loads is really kind of hard to decide. What load should we use as the basis for this stress? Where do we get it from? Do we decide? I jokingly used for, like, we're going to design a chair for an elementary class, right? How big of a kid? How big is the kid should we design for? Right? Well, kids are getting bigger some places, we're gonna have to make some kind of decision. So you're gonna have to, that's just a simple one, right? That's just the weight of the kid. You start to say, hey, how about dynamics? How about a kid, not just the weight of the kid, but how fast they sit down on the chair, right? Are they going to take a flying leap at the thing? And you need a design for that. Well, it's an important thing. I would also say, okay, so another one I decided to put in there was assembly. All right, so I was a marine engineer as my undergrad. I was working in the engine room in ships, and as part of that, we were out at sea for a year as cadets, and I observed a lot of times where we had to put something back together, especially let's say pipes, right? We had these pipes, and we're talking big pipes, and they have flanges with bolted flange joints, and inevitably you take something apart, you try to put it back together, and the line of the pipe, the center lines of the pipe, they're off, and it could be down and over to the side. And what you do is sometimes you even get one of those chain falls, which is like a pulley made of chains, right? And you put it up against the bulkhead, and you make these two things line up with each other, and you put bolts inside there. You have residual stresses that you just placed inside that material right there. Stresses that were not part of the design, right? When we calculated the thing, those stresses weren't there. Many other things like that, where there's like residual stresses, things that might be put into the thing. I also want to say wear and tear, and I use as an example the tailgate on the Chrysler minivans, and I need to look this up to see if I get all the details right in the story I tell, but those tailgates latches started to go after a number of years, and there's responsibility on the engineer's part to try to account for the fact that this minivan was going to exist for a really long time and could be used and abused, and still it's got to function, because the consequences of it not were pretty severe. So like, even end use is maybe kind of a thing that we might want to say, like, how is the thing going to be used over its life? So how do we account for that? We account for that with a design factor, which we define as N subscript D, and that's going to be loss of function parameter over, let me see if I get this right. I'm going to write it maximum allowable parameter. And this is going to be, say, strength, and this is stress, right, or allowable stress. So strength divided by allowable stress. We're going to say, or it could be force. This could be the maximum force the thing can withstand, and this is going to be the maximum allowable force that we could place onto the thing. So here's what Shigley has to say about the static strength, and just questions like, more often than not, it's necessary to design using only published values of yield strength, ultimate strength, and percentage elongation, blah, blah, blah. And how can one use such meager data to design against both static and dynamic loads, 2- and 3-dimensional stress states, high and low temperatures, and very large and very small parts, right? So the variability inside of, like, the thing, but compared to like what we're calculating, it's a little intimidating, right? Because we only use like one number, one value, and that's like strength a lot of times. So that's one of the things we have to use the design factor for. We have the design factor, and as I said, and so I'll make it specific to our, this was more generic right here. This was loss of function parameter and maximum allowable parameter. But they could be all kinds of different things. But here's what we'll usually use. We'll usually use strength over allowable stress. And we'll write it out as ND is equal to strength, and then some subscript divided by this allowable, right? And so we will say this is a design set factor based on yield strength, or design factor based on ultimate strength. It'll be set ahead. But most often what we're going to use this for, even though it's written this way, is we'll rewrite it this way. So we'll get the strength data. We will know the design factor because of a code or a standard or experience or company policy or all kinds of things, hopefully. And then we'll say this is the allowable stress. And then we'll start working backwards to see what we can do, either with maybe make the maximum allowable load onto the thing, or we'll pick the dimensions of the piece, that either or. But that's what the design factor's for. Now, go in the other direction. That was the design side. On the other side might be the analysis side for something that already exists. So we have the factor of safety, which is the second cousin. And you could think of them interchangeably, but they're kind of different. They're kind of different because this is going forwards or actually going backwards from the design and trying to figure out, okay, how to design the thing to be safe. The other is like saying, well, how safe is it, right? So we pick a margin here and we say, okay, this is what we're going to allocate to account for blah, 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 all these uncertainties and other things. Here we go, okay, well, here's the size of it, and here's the strength. So tell me what this is right here. So a lot of times this is going to be, I would actually, well, I'll be careful here. Let me just say that it's like, we'll say the strength divided by the actual stress, right? And so this will often be a way to evaluate an existing design. Or, as we could see in the example that follows right here, that we're going to have, let's say that we pick the diameter of something based on, we know the strength, we have a design factor, and we get this allowable stress, and we work backwards, and we pick the diameter of a rod, right? Well, we need to pick not just some crazy number diameter. We need to pick a standard diameter. So we pick a diameter that's a little bit bigger. Then we can go back and say, well, what's the factor of safety, right? So there was design factor was some value we had. We divided by strength, to say allowable stress, and then we designed the thing. But now we can go backwards and when we pick an actual diameter, we could say, well, here is the strength. We knew what the strength was. Let's divide it by the actual stress, and this needs to be a bigger number than the design factor, right? We will, or it could be some other thing that already exists. We don't know who designed it. It just got designed, and we want to evaluate it, and we'll have some criteria. It must have a safety factor greater than this, right? So two things very, very similar to each other, pretty much. So what design factor to use and what safety factor is acceptable? Those are two valid questions that are very hard to answer because of lawyers, right? We don't want to say, you're not going to see them as much. People will be very cautious about just throwing around what design factor to use or what safety factor is, because something really bad and expensive could happen. And people will trace back, like, where did you get those from? So here's from an old book from 1965. This is a book that I used in college, not in 1965. It was more like 1990. Design of Machine Elements by Fairs. I think it's out of print, but it's a pretty good book. And they did have table 1.1. So you know that it was very in the front of the book, right? And they give you safety factors. But before they do, they give you all kinds of word of caution. And they say, do not use these, right? There's factors of safety marked with asterisk, primary for beginner's use, right? This is just for educational purposes only. Do not design based on these factors and then come back and try to sue us and say, well, I used the values, and don't do it for Dr. Deal. Don't say Dr. Deal told me these factors of safety are okay. These are just to give you kind of a means of comparison look, right? So they said, for factor of safety with a dead load, that means the load got placed really gently onto the thing. It's not dynamic. And based on ultimate strength, they're saying between 3 and 4. Based on yield strength, between 1.5 and 2. Of course, that's, we got to understand, we have to decide what are the consequences of failure is also one of the things that I haven't mentioned yet into here. when human life is involved, we ramp up the design factor and safety factor, right? We say like little kids are involved, right? It's a play set, right? You're not going to call it close. We're going to be very, very safe. Roller coasters, all things that but we'll talk about that in a second. Anyway, you can see like we have other things based on ultimate strength. We have brittle materials, timber. You can see how big that is. It's because there's a lot of variability in wood, right? So we have a large value. You can see for shock, mild shock right here. These are larger values. Anyway, we have shock. We have very large values, right, that we might want to apply right in there. It's mostly because of the uncertainty of like what's actually happening. Because it's very difficult analysis to try to make up. So we try to apply these factors on top of it. So a lot of times we'll do a static calculations. And because we don't know a good way to like model the dynamics of the thing, we'll account for it that way. So these are just some examples. So I read the caption in the table. Good, yes. Should you base from this table? No, right? You should not use this table to design something from. I said, what's the consequences of this design factor being too large? Well, the biggest consequence is that you might be too heavy to do the thing you want to do, right? If you make the plane too strong, it can't fly, right? It might not function properly if you make a safety factor that's way too large. And it might cost too much money, right? You might put yourself out of business because you just designed the thing too, you designed the thing too well. That's really cynical. But you could like maybe make the thing so it's indestructible, so now nobody ever needs to buy another one of them. Or it could be too cost prohibitive, and now you're out of the marketplace because yours cost way more than everybody else's. So that's one of the design. That's the reason why you don't just choose a huge design factor, right? But then what's the consequences of it being too small is lawyers, right? The thing could break, and when it's not supposed to break, and bad things can happen, right? So kids falling out of the back of the minivan. I got some other values. I talked about these in class from other places. I think machine design projects. Is that the name of that thing? Yeah, 1957. I think maybe this is where they're saying they got this from. Maybe. I don't know. Yeah, this guy. Yeah, okay. Interesting. I might look him up, see if I can find this textbook. Anyway, they were talking about various things. And you notice the well-known type of things. Tried, less tried, right? So it's the amount of experience you have, maybe, and a lot with materials. So here's one example here. This video is way too long, but I don't think anybody's going to watch it anyway. And I'll just do Shigley's first, their example 112. And I know I did this in class already. So, but this is just the most basic safety factor thing. So we have a solid bar that has 1,000 inch pounds, and it has that creates a stress, right? So it's being bent. So this is a bending problem right here, right? So we've applied a moment to this thing, and we know that stress can be 32 m over pi d cubed. And if you wonder where that came from, just remember that the I is equal to pi over 64 d fourthed, and stress is equal to mc over I, and we know that C is equal to D over 2, so we just go ahead and apply that there and go, let's see, I'll go pi D cubed over, I did that wrong, boop, sorry, sorry, let's put that I down in the bottom, right, so go pi D fourthed, right, and 64 comes up on top, and then M, and then C is D over 2, right? So boom, boom, that turns into 32. One of those goes away, turns into 3. So that's where we get 32 m pi d cubed, right? That's where they got that from. So they got a strength, I'm going to guess it's yield strength. It looks like a yield strength of 25 KSI. I don't like KPSI, but that doesn't mean KSI, 1000 PSI. And a design factor of 2.5. Determine the minimum diameter of the table, and then use this table A17 to find preferred size, and then determine the factor of safety, right? So you can kind of see how these are used. So what we'll do first is we'll get an allowable stress by taking the strength, dividing by that, and so we get 25 divided by 2.5, and now we're going to say we don't want the stress to exceed 10 KSI. So we'll put it back into this and say here's the allowable is going to be equal to the 32 m pi d cubed. So say 10,000 is equal to 32. The moment we happen to know is 1,000 inch-pounds, so that's fine. And then pi and d cubed. So we can find the diameter from this is 1.006 inches. Just, oh boy, not, it would be nice if it was just under 1 inch or exactly 1 inch. So would you specify 1.006 inches? No. We'd go to table A17. It looks just like this right here. And you'd say, okay, well, someone's going to tell us, should we use fractions of inches? Should we use decimal inches? But you'll see the increment right here. We have 1 and 1 1/4. I almost kind of think 1 1/8 would be kind of acceptable, but they said 1 and between. This is what this table goes strictly going by here. If we go by decimal inches, we could get to 1.2, but we need to round up, right? And we need to give a sensible answer. So D that we are actually to choose, I choose 1.25 inches, 1 1/4, right? This is what I've decided for my design. So now we have to go back and say, okay, well here is that we've designed it. But now let's figure what's the factor of safety? How much factors or a safety factor that we have, right? This was the design factor, remember, right here is what we designed to. But now we want to get what's the actual stress onto this. So the actual stress is going to be 32 times 1,000 divided by pi and divided by 1.25 cubed, right? And we're going to end up with, I didn't write the number down. I don't know why. I didn't get the in-between number. And my calculator ran out. There we go. He's back here. So we have, where'd you go? Pi divided, and so 1.25, 3 raised to there, and divided. So I find that I got 5.215 KSI. I divided by 1,000 in there too. Right? So now we can find the safety factor is going to be the strength divided by the stress, which is going to be 25 KSI divided by our 5.215. So we end up with 4.79. And that is our safety factor. There's the design factor, there's the safety factor. It's a simple thing, but it's a simple differentiation between them, right? Well, it's not that much of a difference, but in terms of words, but it's the same concept. It's just how they're used. Okay, so this is a really long video, way more than I meant to do, but yeah, maybe it'll be useful to someone.